appreciate all of you for joining us in the KPPIM International Webinar 2023 on Mathematical Sciences, Session 8, with our tagline, #Boost Our Visibility. Your presence, of course, is our happiness. My name is Dr. Nur Hazwani Akila Abdul Wahid, and you can call me Dr. Wani, and I am the moderator for today. Before we start our session 8, let's recite Surah Al-Fatihah. Alright, so we are back together in the 8th session. Alhamdulillah, praise and thanks to Allah. Without further ado, please allow me to welcome our two speakers for session 8, which are Dr. SUZILA Muhammad KASIM and Mr. ASROROV USMONOVICH from Uzbekistan. So we start with our first speaker, which is Dr. SUZILA Muhammad KASIM. Let me introduce the biography of our first speaker. Dr. SUZILA has served as a senior lecturer at the University Teknologi Mara, Cawangan, Selangor, Campus Tengkil, Malaysia since 2021. Dr. SUZILA received her PhD in pure mathematics from University Putra Malaysia in 2020. Her area of interest in social network theory, graph theory, and also group theory. She has also supervised 10 undergraduate students for their final project. So please welcome Dr. SUZILA, who will speak for 30 minutes on her research topic, Vertex relation of A sub 4 graph image group, followed by a 10-minute question and answer session. Give our first speaker a hearty round of applause by clicking the clap emoji. So let's click the clapping hand emoji. Okay. So please welcome Dr. SUZILA. You may start your presentation now.
Assalamualaikum and good afternoon, everyone. Thank you, the organizer from KPPIM, UiTM Shah Alam, organized this seminar, and I'm glad to be a part of your speaker. Okay, let me share the slide. Okay, this is our research. Means the is Vertex relation of A4 graph in a mature group. This research is not only my research, not only my research area, but in collaboration with Dr. Shahrudin Jeso from KPPIM UiTM Shah Alam, and also Dr. Siti Noaini Muhammad Aslam from Center of Nation Studies, UiTM Cawangan Campus Tengkil. Okay, let's first see the extract of this study. Analyzing the group structures on a graph can be an effective method which gives rise to many interesting results. And this kind of graph is called A4 graph, which is a simple and undirected graph denoted by A4GX, where G is a group and X a subset of G. This is a set of vertices for A4GX. And connection between two distinct vertices, say X, Y, will be connected by an H if and only if they satisfy this definition XY inverse equal to YX inverse. And this study presents the several properties of A4GX when G is a matrix group M11, and X will be a conjugacy class of element of order 3 in the M11. Okay, let's move to the introduction of this study. Okay, this graph are related to various algebraic structures that has been a topic of increasing interest during the last 2 decades. So there will be a lot of graph has been studied. So this kind of study help us to characterize the resulting result, identify the algebraic structures with isomorphic graph, and to realize the interdependence between the algebraic structure and also the corresponding graph. Okay, let's move to see what is the definition of A4 graph. Okay, A4 graph, we will use G be a group and X be a subset of G. And then the A4 graph, A4GX, is said to be a simple undirected graph and defined on X as the set of vertices in which two vertices X and Y are adjacent if follow the condition XY inverse equal to YX inverse. The study of A4 graph is quite new, and it is proposed by Albert 2021 to be a simple undirected and also a regular graph. And from the study, X is adjacent to Y, and then the subgroup will be generate a group of that is isomorphic to an alternating group of degree 4, which is A4. Okay, here I show you the objective for this talk. For the first objective is we will determine the diameter and the structure of A4GX. G is from the magnitude M11 and X is a conjugacy class of order 3. And to be specific, it is in class 3A. And then to classify the CGT orbit representative in each this data IT, to identify the neighbors of vertex X from the subset, which means the conjugacy class X, and then construct the collapse adjacency matrix or collapse adjacency list. Okay, here are some previous study that related to this A4 graph. Okay, from the from Albert 2021, who has proposed this graph. The study describes certain features of A4 graph when G is an exceptionally tight group of characteristic 2 and X is a conjugacy class of order 3. And two vertices, distinct vertices, will be adjacent. Group will be generated, which is that is isomorphic to A4, the alternating group of degree 4. Okay, here is the proof from
sorry for interrupting you, Dr. Suzila. Dr. Suzila, can you hear me?
Yes, I can.
Dr. Suzila, we cannot see your face.
Oh, okay. Let me check. Okay, pardon me.
Dr. Haswani, something with your computer maybe. We can see clearly, no problem.
Can anybody see my face?
Sure.
Sure. Okay. Dr. Zwani, is it okay? Okay, let me okay. Okay, we continue. Okay, may I continue, Dr. Azwani?
Yes, you make continue your presentation, Dr. SUZILA.
Okay. For the proof from Algebras 2021, okay, the well-known presentation of A4 is given here, and then X and Y have the order 3, and y inverse equal to yx inverse from the definition. Then we will have xy inverse equal to y from this definition. So if we let x equal to z from the Algebras 2021 and y inverse equal to w, and A4 graph, A4 graph, or I mean that subgroup of A4 is generated. From the study of Algebras 2021, the graph is said to be connected. So that's why the graph will have obtain the diameter, and then the further study has shown about this structure and also the CGT orbits of A4GX. Okay, another study from Oda and Albert in 2021. The investigation is on the diameter, the structure, clique number, and girth of the graph A4GX for each lattice group. And also this graph is connected from two type of graph, and one is disconnected. Okay, the first graph is connected when G is HS from the least lattice group, and X is in order 3. And the other one is connected when G is a McLaughlin group, and X is in class 3B. But the graph is disconnected when G is McLaughlin and X equal to 3A in class 3A. Okay, another two research on A4 graph is from Sherry, Abed, and Abid, whereby they study determine the diameter, this structure, clique number, and girth of A4 graph when G is either T group, T, or mature group N20. And both having G conjugacy class of order 3. So consider both with class 3A. And
excuse me, Dr.
Yes,
SUZILA.
Yes.
Regarding order, the order, what does it mean? The order of order is 3A, order is 3B. What does it mean?
Okay, the meaning is we work in the permutation group of order 3, and then the class of 3A, 3B is classified from the main website of Atlas of finite group that define for representation 3A, 3B, and so forth. They are still in order element of order 3.
So that means the X is all elements of order 3 in that group.
Yes.
So that is denoted by 3A.
Yes, from the permutation group.
Okay, thank you.
Okay, welcome. And then Al-Adami, Majid, and Aubat 2022 recently present the diameter, this size, clique number, and girth of A4GX that have been determined when G is the head group, and also X is considered of order 3. And this study use class of 3A and 3B.
Sorry, what's the A or the B there?
Okay, 3A and 3B Later I can show the website of the Atlas of Finite Group, and then the listed conjugacy class will be particular in 3A, 3B, and
So you mean there is a classification of finite groups. So from that classification, you are just looking at that class which 3A and the 3B.
yes, yes,
Am I right?
yes.
So how many classes in that classification? Say each, because each if you have finite group with a fixed order,
Yeah.
then you have finite number isomorphism classes, right? So which dimension, which order you are looking for? Which dimension is fixed there? Say, I mean order of the group, or say order of 4, 5, 6, and so on. What do you mean in 3A or 3B? In which order? Your group order. Because your group's classification depends on how many classes there, depends on the order of your group.
Yes.
So that's why for each order, that notation must be different. So what do you mean in 3A, in the 3B? What does it mean?
Okay, 3A, 3B are they are conjugacy classes element in order 3, but the conjugacy they are different between the structure of conjugacy class from each other, 3A and 3B. Might be, for example, if we have symmetry 9, it can
is your group fixed?
I use group M11, Mathieu group.
That finite group, which order? What's the order of your group? Mathieu group order?
The order is about 4. The order of the group is 4032, if I'm not mistaken. It's about 440 multiply 18. That one is the order of the group. But 3 is considered the element in the of the conjugacy class.
Yeah, you are mentioned here M20 is a Mathieu group, right?
Yes.
So the order of that Mathieu group M20 is 4032 or something like this, right?
Yes.
So you are fixing that group as a G.
The group is G, Mathieu group. So
Yeah.
M11.
You will take G as a Mathieu group, right?
Yes.
So there, that in Mathieu group, we have classification. One of classes is denoted by 3A, another class is 3B, or how? It's not so clear that your
for example, I give let's say the group is symmetric group 6, for example. Okay. I will put a symmetric group of 6 for to be
S3.
Yes, S6.
S3, because S6 is 6 factorial. S3 is 3 factorial, which order is 6.
Okay, S3, so among that, the elements of order 3 will be 1, 2, 3, 1, 3, 2. The permutation group in the S3. Or later, I will give some simple example for the permutation group. Is it okay, Prof?
Yeah, it's okay. Just continue, no problem.
Okay. So, okay. Later, I will brief about those elements in that group. Okay, let's move further. These are the ingredients because of this is the graph group. So the ingredients need group theory definition. So part of them, of course, we need to know what is the group, and then simple group, which means that mature group will be part of the simple group, and then this group, this study will be on the group action, and then we will study on the orbits of the group G, and of course, permutation group will be involved because of the conjugacy class to be the subset X from the group G to construct the graph A4CX. And then this is definition of alternating group, where A4 is generated when two vertices are connected to each other, and also conjugation definition is needed as well, where we have the conjugacy class element inside. Okay, the next part will be the graph redefinition. This study is about the simple graph, and later we have to know what is the degree of Vertex, because of this study is about the transitive Vertex of this graph, and then distance between two vertices are required to define the diameter of the graph. So here we have the diameter of the graph, and then before we define for the collapse adjacency metric, we have to know what is the adjacency metric, and then come up with the collapse adjacency metric. The difference between them are adjacent metric, the interaction between one vertex to another vertex, but collapse adjacency metric will be connection between one orbit to another orbit. So it will link on how many vertices connected between them. Okay, in the methodology part, our computation will use magma because of the size or the size of the group, and also the elements involved there is quite big, and this is the magma. We can see that this I show you the web link, and then there is a simple calculator that might be some of us would like to try first before we make some pictures here. And then for the all those representation is is taken from this web, which is the atlas of finite group, where we take all of the notation of the mature group and the conjugacy class, and all the information are given here. So we will click later in the sporadic group, we will find mature group and 11, and it will appear the information needed. And also include the magma coding. Okay. Before we do make construction of A4GX, so this study will we will assume that the element of X, and then we have delta IX to identify the IDs of X, which means that how what is the distance between from one fixed point T from that group G into that disk. So let's say that this is delta 1x, means that they are distance 1 between the given T from the G. And then this will be give the definition for the delta IT or delta IX, and distance here will be the standard distance metric for the A4 graph, where we use the distance definition from the graph theory, and the fact that G is transitive in A4 graph vertices, and acting on X by conjugation, and also into the A4 graph automorphism group.
Excuse me, Dr. SUZILA, something is confusing here.
Mhm.
In your definition, delta I,
Yes.
left side depends on I, but the right side doesn't depend on I. Something is wrong there.
Okay, let me check.
Or this is implicitly, maybe X
Oh.
implicitly depends on I because where is X?
I may say that
Because
this
X is any element of X.
yes.
Y also is element of X. They don't depend on I. But left hand side depends on I. Something is wrong there. Maybe that instead of 1, maybe must be I.
Yes, Prof.
Ah,
Yes,
so distance between X and Y must be I. In that case is correct.
Yes. Thank you. Okay, then the construction of A4 graph. Okay, on how we start to construct this graph is, since our group is M11, and we will the one of the element from the group M11, which is in this order. So this type is in class 3A because of this permutation group is order 3 and having this 3 cycle here. So this type will be 3A. If I'm not mistaken, for example, permutation 12, one class will be having 3 cycle, and another class will have 4 cycle. So they are different between how many cycle they have from the 3A from one class to another class with the same order. Okay, we have defined what is the group, and then we have taken the random element of order group of order 3, and for this process, we need the order of conjugacy class of G, and also the order of centralizer from this group, and we start to find set of element which is having distant 1 from the given element D. So that's why we put D1, means that distant 1 from D. So later we will find how many order of the set, instead how many vertices inside from the set of element D1. Okay, for the rest, to find distance 2 and onwards, so we will proceed with this segment so that use this definition, and we will see what is the set element for the I, which means the I from 2 until K, and the I will be the set of the order of the set given. And the last part will be we do some the order of the set element from the T to dk up to dk to ensure that they are all equal with the order of conjugacy class of G.
Excuse me again. What's the K?
K is distant K from T.
K.
We may say that it is the diameter of the graph.
Okay. Thank you.
Delta KT, delta KX.
Continue, please.
Yes?
Yeah, okay. Continue, please.
Okay. Okay. Since we use a 3 cycle of permutation group M11 with T order 3. I will give simple example using the same algorithm, but I choose G as symmetric 5. So let's see the order 3 with the only in one cycle is for example 3 is 3, 4, 5, and then we know that it is X will be conjugated with G. Okay, later we will have around 20 elements for X, 20 elements in conjugacy class X. So that the total vertices in that graph must be 20 from T up to in the last disk for the graph. Okay, given the order is 20 of X, order of CGT is 6, and altogether for S5 order is 120. Okay, we still implement the same algorithm. Later, what we have is since we choose T to be 3, 4, 5, and using the algorithm, we may have some vertices in data 1T, some in data 2, and a vertex in data 3. So we will define the XY inverse, Y-axis inverse, so that from T3, 4, 5, so for those this element putting in the data 1T. Instead, from this vertex or 0, 1 vertex, we connect to 0, 2, connect to 0, 3, 0, 4, up to 0, 7. Okay, later, to find the element in data 2 and data 3, okay, since we know the vertex 0, 2 is already connected to 0, 1, so it will be connect to some element in data 1 and then some element in data 2 as well. So here we list down the element in data 2, and the remaining is only one vertex in data 3. So for this graph of G symmetric 5 with the T 3, 4, 5, the diameter is 3. And I will show you the interaction, part of the interaction of this graph, so that since this is the conjugation action and then conjugate on the graph, we can see that vertex 0, 1 will connect to 6 vertices. Means that all other vertices means that each vertex will connect to another 6 neighbors, another 6 vertices among them. For example, 0, 2 will connect to 0, 1, 0, 3, 0, 4, and then 0, 8, 15, and also 19. The same, and all each vertex will do the same, having degree 6. Okay, so here we come to the result of the study. Let's see the diameter of the A4 graph. Okay, for the graph, we move back to the group M11, and as in the class 3A, as we have the element and the 3 cycle of order 3, then the graph of A4, sometimes we put GX, sometimes we put exactly M11 and 3A. It will have diameter exactly 4. From the algorithm 1, and also the table 1 given, the given data here are all order of each set of these. The delta 0 T means that it will be equal to the T itself, the vertex that we put as the starting point, and then distance 1 from that vertex T, we have 18 vertices. Distance 2 from T, we have 4 vertices. Distance 3 to 6, and distance 4 will have 11. So we will make sure all this will be 4 all vertices and relate to the order of the conjugacy class X. So when the diameter, when the distance is div or delta 4, so we may conclude that the diameter of this graph is equal to 4. Okay, the other result of this study is on the CGT orbit representative. So CGT orbit representative is calculated from the double coset from two subgroup, CGT, centralizer, and then from the calculation, we may have the CGT orbits include the element T itself. So, for example, from number 1, this is the T, the element T, and then from the number 2 and onwards, x1 means distance 1 from T, and then comma 1 means that the first orbit in this. So this CGT orbit will be union delta IT will be union of CGT orbits. And then this CGT orbit are made up of 1 from the T, 1 orbit from the delta 1, 8 orbits from delta 2, 18 orbits from delta 3, and 2 orbits from delta 4. So the list here we have up to 30 orbits. Okay, when we see about the next part is the neighbors of a vertex X. Of course, the graph is regular, so it may have the same degree from each vertex. The proof given here on how the connection between, for example, with T with those element alpha 1, alpha 2, 3 until alpha 9, and then since this group is M11, and then we choose the points up to 11 only. So means that alpha and alpha 11 both in fixed point. Okay, let's say another element will be in term of beta. The permutation of X will fix beta J. As I said, that will be J will be the fixed point of this T. Okay, later we will see that we will connected to another element. See that element in delta 1, so that one of the fixed point J will be in the element in delta 1. So that T in that element will be connected. Might be T will be one of the fixed point involved that connected to T, and another permutation will involve 11. So 10 and 11 will be separated. Okay, so according to theorem 1, this graph is connected. So that's why we find the diameter, and any vertex could connect to multiple vertices from the same delta IT or to the other this. And then when we consider this group, its order of CGT is 18, that match to the number of vertices that connected to X. Okay, for this case, the degree of the vertex is 18. So that T will connect to 18 vertices in delta 1 and one vertex in data 1 will connect to another vertex, total 18, include T, some in data 1 and some in data 2, as long as they are in distance from each other. Okay. In addition, the number of adjacent vertices to X is determined by using the fixed point of a permutation of X, as I mentioned earlier. And then clearly, X produces fixed point Bj. Thus, 18 connected vertices are categorized as follows. Since there are two fixed points involved in the permutation X, the permutation are split into two parts. Each part will have 9 vertices and acquire a fixed point beta j. So this is how I mentioned. And then while the other fixed point interchange between beta 1 to beta 9 for vertices to another vertex. Okay, and then each X can only be connected to 18 vertices in graph A4. So the degree for each vertex is only 18. Consider the order of the CP orbit. Consider for the centralizer. Next is the collapse adjacency list. We may construct collapse adjacency matrix, and if it may use some space, so we may change to collapse adjacency list. Just to list down which orbit connect to which orbit and how many edges involved between them. Okay, for example, 1 here, the number 1 here will give, this is orbit from number 1. So we will back to here. We will follow the number here, 1, 2, 3 here, up to 30. So for example, 1 and 2. Okay, orbit 1 for I1 will connect to orbit 2. So edges will exist between their interaction. And then, for example, from the 2 will be back to 1. So, yeah, Dr. Oswani. Okay, and then we may consider the other orbit, for example, in this pink part here, from the orbit number 2, which means that this is orbit from data 1 and connect to orbit T. So of course, it's just only 1. So connect with the same orbit in the same only 2 edges exist and so forth. Okay, here are the how we show the collapse adjacency list. The connectivity between two vertices could be fulfilled the definition of the graph. Okay, we may use the collapse adjacency list or the square collapse adjacency matrix of order 30. So we start 30 by 30. And then each line of the collapse adjacency list display the list of the orbit as I mentioned earlier. And then we will give how many iterations involved, how many edges. And between a vertex UI with the conjugate element of UJ, the interaction between these two representatives could be measured. So from our observation, the list will give us 3 to 2 from the 900 entries, and the rest will be in 0 entries. Okay, now we come to the conclusion for this study. The graph can be performed with X of order 3 when G is M11. And in this study, the diameter and the structure have been determined. It is followed by classifying each data IT into some CGT orbit using the double coset. So besides that, each vertex possesses the same number of neighbors because this graph is regular and this graph is said to be regular. The interaction between two CGT orbits can be seen by constructing either collapse agency matrix or collapse agency list. And then in future, since some previous study and our study involve element of X in order 3, so the greater order of X can be considered using the same graph later. Okay, with that, thank you. Back to the assignment.
Alright, so thank you very much, Dr. SUZILA, for your interesting presentation. I would say this is an interesting presentation about the you are constructing the A sub 4, right? A sub 4 graph in a Mathieu group. So let's move on to the next session, which is the Q&A session. So now we will open our Q&A session. Please feel free to leave a comment or you can speak up directly. So please, anyone, you can ask any question to Dr. SUZILA.
Dr. SUZILA, that magic group is simple group, correct?
Magic group?
Simple.
Magic, yes.
Is it simple?
Yes, yes.
A subgroup of what? Which group? Which symmetric group? S9?
This one we consider S11.
S11, but you are taking cycles, 3 cycles there.
Yes.
So that means another 2 elements, 10 and 11, they are identical, right?
Yes.
Why you're taking this type elements only? Do you have any order 3 elements of order 3 which are different from your three cycles, product of 3 cycles?
For M11, only one class we have, 3A. But for
conjugate class.
Yes.
Conjugate. Huh?
Yes. For another matrix group, for example, M12, M21, and 22, 23, then we have more than one. Instead, might be 3A, 3B, and up to 3C, 3D.
Okay, so we are considering only M11, not other orders?
The rest are still in working for the still in matrix group in the different point.
Okay, jumping from one to another one, do you have anything new to create? A new idea? Or you just considered symmetric group S3, right?
Yes.
Your previous research was related to S3. Then you jump to Mathieu group. So jumping, this jumping motivated by which kind of idea? Do you have any idea or the same method, the same methodology?
Oh, yes, Bob, the same methodology. If previously I do study on commenting graph, and this time I do A4 graph. So just to see that are they connected or disconnected, and what are those other further properties that we can find other than I did now. Might be the Gauss, the click number, might be some relate to chemical indices, for example, Sombo index, Wiener index, and so forth. Might be can consider.
Is Mathieu group related to that applications?
In terms of structure,
Were you taking method group, not other groups? Because finite groups a lot.
yes.
Finite simple groups, they are fully, completely classified. So
Yes.
that's why even it was calculate their conjugate classes also.
Yes.
So that's why just I wonder where is novelty here in terms of new idea. What is a new idea to study?
Okay, Prof. I will consider the might be the other group, maybe the outside of the simple group. For the future study.
Okay, thank you.
Okay, thank you, Prof.
Dr. Suzila,
Yeah.
can we have say if we, instead we have A sub 4 graph, can we do for A sub 2 or A sub 8?
Okay. Those A sub 4 instead it is in the group alternating group degree 4. Okay. Instead the connection between them will connect will be generate that group A4. And we may consider, and from the previous study of mine about commutative graph, we did on subgroup generated, that one from the commutative graph. So we will see later rather than A4, might be we may consider another non-abelian group involved there. Not only A4, it will be A5, A6, and will be some other order of the group from the group generated between two vertices.
All right, so thank you, Dr. Suzila. So anyone have question? Okay, I think we should move on to our second speaker. So thank you very much, Dr. Suzila, for your answer to the question. So for our second speaker, we have here Mr. ASROROV DIYORJON USMONOVICH from Uzbekistan.
Just Mr. DIYORJON.
Sorry, Prof. Mr. DIYORJON.
DIYORJON,
Right.
because ASROROV is a family name.
Oh,
First name is DIYORJON.
Okay. Thank you, Prof. Mr. DIYORJON. Right. So Mr. DIYORJON is a PhD student in mathematics at Samarkand State University, Uzbekistan. He completed his bachelor's and master degrees in mathematics from Samarkand State University, Uzbekistan in 2019 and 2022, respectively. He has also been an intern researcher at Samarkand State University since 2022. So without further ado, Mr. DIYORJON, please give your talk on a complete classification of two-dimensional Endo-commutative algebras over an arbitrary field for 30 minutes, followed by a 10-minute question and answer session. So please, participants, give a big clap to our Mr. DIYORJON. All right, clapping, so please clap, everyone. So thank you.
So, Assalamualaikum. Today I want.
Sorry, Mr. DIYORJON. We can see your face, but your face is cut half only, half of your face. Maybe you can your screen. Turn on your screen. All right. So thank you.
Can you see?
Yeah, no problem.
Today I want to talk about a complex classification of two-dimensional endo-commutative algebras over an arbitrary field. So my report plan, abstract, introduction and motivation, preliminary necessary results, methodology and results, main theorems, conclusion and reference. So abstract. In this talk, we consider the class of so-called endo-commutative algebras from the identity imposes that specify this class. One can easily see that the product in this class preserves the square of elements. We give a complete classification of this class up to isomorphism over any basis field in dimension 2. This elementary and self-contained exposition uses the present result of one of the authors on description of the category of all two-dimensional algebras over any basis field. Introduction and motivation. The classification problem up to isomorphism of given class of algebras is one of the important and difficult problems of algebra. So far, two approaches are known to solution of problem. One of them is structural, basis-free invariant approach. For instance, the classification of finite-dimensional simple and semi-simple associative algebras by Redborn and simple and semi-simple Lie algebras by Cartan are examples of such approach. But it is observed that this approach becomes more difficult when one considers more general types of algebras. Other approach to the solution of the problem is coordinate-based. Many researchers have used this type of approach to classify variables, mainly finite-dimensional class of algebras, associative, Lie, Jordan, and Leibniz. These two approaches are somehow complementary to each other. Recently, in a paper, a complete classification of two-dimensional algebras over any basis field has been announced, and we have come across with the paper 26, where the authors gave a complete classification of two-dimensional endo-commutative algebras over the field Z2. We have realized that it can be done over the arbitrary field by more easy and faster way, relying on the results of 5 in this subject of present paper. Preliminary necessary results. Let A be n-dimensional algebra over a field F and E be basis of underlying vector space of A. Then on the basis E, the algebra A is represented by n by n square matrix. This matrix, they call it matrix of structure constants, shortly MSC. These elementals call it structure constants. As follows, here we can see times basis elements, and therefore the product on A with respect to the basis E is written as follows: 2.1. Here we can see x times y equal EA, x tensor product y for any xy. If A is two-dimensional algebra over a field F and E equal E1, E2 is a basis, then matrix structure constants of A looks like this: 2 by 4 matrix. Here structure constants alpha 1, alpha 2, alpha 3, alpha 4, beta 1, beta 2, beta 3, beta 4. In 5 paper, the following classification up to isomorphism of two-dimensional algebras over any basis field F in terms of their matrices structure constants was given. According 5 paper, we can take these 3 theorems. Theorem 1, any not trivial two-dimensional algebra over a field F which characteristic F is not equal to N3 is isomorphic to only one of the following listed by their matrices of structure constants algebra. Here we can see certain classes algebras and theorem 2 here characteristic F equal to, here we can see 12 classes algebras, and theorem 3 with characteristic F equals 3. Here we can see certain classes of algebras. In the next section, we classify up to isomorphism various classes of two-dimensional algebras over any field relying on these results. Definition and the commutative algebras. Definition 1. An algebra A is said to be endo-commutative if this equation holds, where x squared times y squared equal x times y in brackets to the 2 for any xy, here xy n elements A. According to 2.1, we can write this equation tensor product form, because x squared equal this EA x tensor product x and y squared equal EA y tensor product y, and etc. Here we can see the equality x squared times y squared equal x times y in brackets to the 2 in terms of matrices of structure constants, and the coordinate vectors is written as follows: 3.1. And let A be two-dimensional algebra over a field F, and let this matrix 2 by 4 matrix be its matrices of structure constants on a basis E1, E2. So we can rewrite this equation 3.1 and we take this system of equation. Here A3, A4, A5, etc. be 14 equal this. Here alpha 1, alpha 3, alpha 4, beta 1, beta 2, beta 3, beta 4 matrices of structure constants. Here we can see functions. Here has got 8 functions, and note that the set of the functions, these functions, is linearly independent Therefore, this system 2.3, this system 2.3 3.3 can be rewritten as follows: 3.3, this form. The equation 3 and 8 in the system can be removed since they linearly depend on the remaining equations, because we can see third equation A6 and A4. We can see this second equation and A11 minus A13. We can see a fifth equation. For that, these equations linearly depend in others equations. In terms of structure constants alpha I, beta g, the system 3.3 is written as follows. This system is follows. Here we can see 8 equations, system of equations, and according this system of equations, we can give classification in the commutative algebras. It is clear that in this case, to get classification of two-dimensional Endo-commutative algebras, it is enough to solve general system 2.3.4 for each matrices of structure constants AI of the algebras in presented theorem 1. In theorem 1. We see in theorem 1 has got certain classes. We started first class for A equal A1. In system of equations 3.4, we can see has got structure constants A1, A2, A3, A4, and B1, B2, B3, and beta 3 in beta 4. And here we can see A1, alpha 1 equal alpha 1, alpha 2 equal alpha 2, alpha 3 equal 1 plus alpha 2, alpha 4 equal alpha 4, and beta 1 equal beta 1, beta 2 equal minus alpha 1, beta 3 equal 1 minus alpha 1, and beta 4 equal minus alpha 2. According this, our system of equation 3.4 looks like this. Here we can see 8 equations, and simplifying we get this system of equations. Taking into account the third and fifth equation, we obtained there we can see third equation alpha 4 equals 0 and 5 equations beta 1 equals 0. Using this, we give this system of equations, and as far as the second and fourth and eighth equations, second equations and 4 equations and 8 equations show inconsistency of the system. This system. So there is no Endo-commutative algebras in this class of algebras. Similarly, if a second class of algebras, A equal A2, our system of equations looks like this. Here we can see first equation alpha 4 equals 0, and this is our only solution. And for here our solution alpha 1 alpha 4 equals 0, for that alpha 1 0 beta 2. This is the only solution this system of equation. If A equals third class of algebras, our system of equation looks like this, which has only the following solutions: alpha 1, 0, beta 2, and 1 over 2, alpha 4, 1 over 2. These are our solutions. In first class, a system of equation looks like this, and we can see this 2 equals 0. For that, this system of equations inconsistent. If A equal A5, the corresponding system consists of identities. All the algebras in this class are endo-commutative. In sixth class, the system of equation looks like this, and the solution to the system is alpha 1, 0, where alpha 1 an element f. Seventh class, if A equal A7, our system of equation looks like this. Obviously, here we have two solutions. First solution alpha 1, 0, and second solution 1 over 2 alpha 4, where alpha 4 is not 0. If A equal A8, where beta 1 is an element F, it is easy to see here the system is inconsistent. Verifying the system of equation 3.4 for A9, A10, A11, A12, and A13, we get identities. All these algebras happen to be endo-commutative algebras. So the final result for algebras over a field F, which characteristic F is not equal to N3, is given as follows. We have this theorem, theorem 4, any non-trivial two-dimensional endo-commutative algebra over a field F, which characteristic is not equal to N3, is isomorphic to only one of the following listed by their matrix of structure constants, such algebra. Here we can see 12 algebras started A2 and last one A13. Second case, if characteristic F equal 2 or characteristic F equal 3. As for description of two-dimensional endo-commutative algebras, in characteristic F equal to N3 cases, it can be obtained relying on the corresponding theorems 2 and theorem 3. Here we present corresponding results without proof. Theorem 5, here we can see characteristic F equal to in theorem 2 has got 12 classes of algebras. According 3.4 system of equation, we get these results. Here we can see 11 classes of algebras. Next theorem, if all field F equal Z2, a case the theorem above can be stated in more detailed form as follows. Only 3.1. Here, any natural two-dimensional endo-commutative algebra over a field F equal Z2. Here we can see classes of algebras. 18 classes of algebras. Next theorem. In this theorem, characteristic F equals 3, and we can see there 11 classes of algebras. In next case, in 26 paper, the class of endo-commutative algebras was split into two, correlate and straight algebras. There one can find a list of such algebras up to isomorphism over the field F equals Z2 as well. In this section, first we classify all two-dimensional correlate algebras. Then, by use of previous sections results, we give the classification of all endo-commutative correlate algebras up to isomorphism over any field F. Definition 2. In algebra A, or a field F is said to be correlate if this equation holds. X square equal lambda x times x for any x, where x an element A, and lambda x an element F. According to 2.1, we can write x square equal EA x tens the product x, and lambda x times x equal E lambda x times x. And therefore, the equality x square equal lambda x times x can be written as follows. 4.1 equations. Consider two-dimensional case. One has these bases and these matrices of structure constants. Here we can see prime. Every element has got prime, and according Z, equations 3.4.1 becomes this system of equations 4.2. We consider two options. 4.2. First, let lambda x be not identical 0 over f square. Then it is easy to see that here two cases. First case x1 equals 0. Here three cases. first case, x1 equals 0, x2 is not 0. Second case, x1 is not 0, x2 equals 0. And third case, x1 and x2 is not 0. If x1 equals 0 and x2 is not 0, we implement alpha 4 prime equals 0. And lambda x1 0 equal alpha 1 prime x1. If x1 is not 0 and x2 equals 0, according 4.2 this system of equation, respectively beta 1 prime equals 0, because here we can see x2 equals 0, x2 equals 0, this all of this equals 0. We have beta 1 prime and times x1 square. Here we can see x1 is not 0. For that, beta 1 prime equals 0. And lambda 0 x2 equal beta 4 prime x2 times x2. Therefore, 4.2 system of equations can be rewritten as follows. And here we have two cases. First case, if f or field is not equal z2, then at least of alpha 1 prime beta 4 prime is not 0, and our algebra looks like this. If our field f equals z2, here we can see alpha 1 prime is not 0, and a minus beta 2 prime minus beta 3 prime is not 0. And our algebra looks like this. Second options, let lambda x be identical to 0 over f squared. Here, in this case, the system 4.2 is equivalent this. Alpha 1 prime equal alpha 4 prime equal beta 1 prime, beta 4 prime equal alpha 2 prime plus alpha 3 prime equal beta 2 prime plus beta 3 prime equals 0. And therefore, we have this type of algebra. We said this type of algebra to zero patent. About these algebras, we can see these papers 9, 16, and 17. Science, we know for two-dimensional algebra given by matrices of structure constants A to be correlate algebra, we can treat the description of two-dimensional correlate algebras by using theorem 1, theorem 2, and theorem 3. For example, if our characteristic f is not equal to and 3 in theorem 1, given first class A equal first class A1, here this algebra is correlate algebra if and only if it has following form. here alpha 1 equal alpha 1 prime, we take this system equation alpha 2 equal alpha 2 prime and 1 plus alpha 2 equal beta 4 prime minus alpha 2 prime, alpha 4 equals 0, etc. We can give this system of equations, which happens if and only if alpha 1 equal 1 over 3 and alpha 2 equal minus 1 over 3, alpha 4 equals 0, beta 1 equals 0. Therefore, among the algebras A1, only this algebra is correct. Going through A2, etc., A13 in this manner, in theorem 1, one commits following classification results. Theorem 3, Theorem 7. Any non-trivial two-dimensional correlate algebra over a field F, which characteristic F is not equal to N3, is isomorphic to only one following listed by their matrices of structure constants. Such algebras. Here we can see third class of algebras. Among the listed algebras, only A3 0 0 minus 1 is zero patent algebra. Similarly, in characteristic F equal 2 and characteristic F equal 3 cases, the following results are valid. In theorem 8, characteristic F equal 2, here we can see third class of algebras, and here only one algebra is zero patent. It is A3 to 0 0 1 algebra. Next theorem, if a field F equals Z2. Here we can see 6 classes of algebras, and among these algebras, only one is zero patent. It is A3.2. Second class, if alpha 1 equals 0, it started zero patent algebra. And theorem 10, here characteristic F equals 3. Here we can see third class of algebras, and here one algebra is zero patent. It is A3.3.002 algebra. Main theorems. Now one can use the results of last two sections to get classification of two-dimensional endo-commutative correlated algebras up to isomorphism. Theorem 11, any non-trivial two-dimensional endo-commutative algebra, correlated algebra over a field F, which characteristic F is not equal to N3, is isomorphic only one the following listed by their matrices of structure constants, such algebras. Here we can see two classes of algebras. Among the listed algebras, only one is zero patent. This algebra is zero patent. And next theorem, characteristic F equal to and F field F is not equal Z2. Here we can see two classes of algebras, and here one zero patent algebra. Next theorem, if our field F equal Z2. Here we can see 7 classes of algebras in one zero-patent algebra. Note that the endo-commutative correlate algebras given is 26 paper can be found in theorem 30 as this. And last theorem, theorem 14, any non-trivial two-dimensional endo-commutative correlate algebra of a field which characteristic F equals 3 is isomorphic only one following listed by the matrices of structure constants such algebras. Here we can see 2 classes of algebras and one zero-patent algebra. And conclusion, in conclusion, we have given the following results here. We give 3 results. First, a complete classification of two-dimensional endo-commutative algebras over an arbitrary field. Second, a complete classification of two-dimensional correlate algebras. And finally, we give a complete classification of two-dimensional endo-commutative correlate algebras over an arbitrary field. Here references. Here we can see second.
All right. So thank you very much, Mr. DIYORJON, for your fascinating presentation about the classification of two-dimensional endo-commutative algebra. So please, anyone has questions, so please ask Mr. DIYORJON. You are welcome to ask any question to Mr. DIYORJON.
Can I have a question, please? Okay, Assalamualaikum, Mr. DIYORJON.
Salam.
Okay, I want to ask, how do you get the calculation? You do it manually or you put in some mathematical software?
Please, can you repeat? I don't understand.
Okay, about the calculation. Okay, how do you get it? Do you do it by manually or do you put into some mathematical software to check the answers?
Let me explain the question. Dr. Renesis want to ask you, siz qo'lda qilganmisiz yo qanaqadir programmada qilganmisiz deb so'rayapti. Sorry.
I do it by myself.
Qo'lda qilganmisiz yo qanaqadir programma qo'llaganmisiz deb so'ralyapti.
It is work. We don't use programs. I do it by myself. I write this.
I see, Mr. DIYORJON. I think you solve the system manually, is it, without using any computation
No, no,
software?
no.
So Dr. Rini, is it answer your question?
Yes, yes.
So, Mr. DIYORJON, I myself also wanted to ask you question about what does it mean by zero potent? Does it mean that the element in your matrix you have zero element, at least one or two zero element for the zero potent?
Just a minute. Here we give definition zero patent algebras. If our algebra looks like this form, is called zero patent algebra. First element 0, here alpha 2 minus alpha 2, 0, 0 beta 2, and minus beta 2, 0. This type of algebras said zero patent algebras.
So the zero potent means all the elements must be zero. Is it?
No, no. Yeah, no. Here we can say alpha 2 prime and beta 2 prime. These elements can be 0 or can be not 0.
Not zero.
For example,
8 element there. So one column, first column and the last column are zeros.
I
But another two columns, you can see that there are relations between them. So one second column is minus of third column. If you have such kind matrix of structure constant, that algebra is called zero potent algebras. So that is zero potent algebra definition.
Sorry, Prof. If we have the first and the last column, all the elements are zero, isn't it?
Yeah.
Okay. So can I see the next slide? You conclude that all the elements you consider as zero potent. Among the listed algebra. So how about theorem 8? Theorem 8, if we see there are three matrices there, but the first column and the last column for A12 is not zero. So is this a matrix we consider also as zero potent?
No. For example, theorem 7, we can see second class, and here we write A3 0, 0 minus 1 is zero patent. Here we can see alpha 1, so alpha 1 equals 0.
I see. You substituting alpha sub 1 0, then we said that the A3 is zero.
Yes.
Okay, so we
If
have
alpha 1 equals 0, this algebra is zero patent.
I see, because we after we substituting the alpha sub 1 equal to 0, then we will have the first column and the last column, all the elements are 0. Okay, now I know.
Yes.
So thank you, Mr. DIYORJON. So any questions from the other participants?
Assalamualaikum. Is your F is measurable field?
Sorry?
Is F a measurable field?
No, here field F, any field.
Is it measurable?
It's not topology here.
It's not topology.
It's not topology. Any field. Only
Any
characteristic must be not 2, 3, characteristic 2, and characteristic 3. Then the measurability is with topology or some matrix. Not any topology in F.
Okay. Could you give a definition of the character of the field?
Character of
Or could you give an example field with character 3?
You will take 1, add several times. If it is 0, as a result is 0, then that field is called finite characteristic. Characteristic can be only prime number, 2, 3, 5, and so on, or 0 characteristic, where adding 1 easy time, you will never get 0. In that case, characteristic is called 0. Other cases, if you have some finite number, adding 1 several times, then that field is called finite characteristic. So here we are distinguishing two cases, characteristic not to 3, that means any, or characteristic 2. That means in that field, you adding 1 to 1, you will get 0, characteristic 2 case. Characteristic 3 case, you add 1, 1, 1, you will get 0. Say Z3 is characteristic 3, Z2 is characteristic 2.
Yeah.
That's examples of 2 and 3 characteristic. Complex numbers, they are characteristic 0. Real number, characteristic 0. Rational numbers, characteristic 0, and so on.
I see. Thank you.
Because this one is our joint result, joint paper with Dr. Ural and DIYORJON together. We are 3 authors. So that's why I have right to answer your questions also.
Thank you.
You're welcome.
Thank you, Professor.
Okay, I think we should proceed to the next session, which is the photo session.
Dr. Hazwani, just
Yes,
a few words. I want to just give some comments here.
Yes.
In fact, the motivation to study this case is given by a result of some Japanese mathematicians. Can you open the references, DIYORJON? Number 26. Here you can see the classification of two-dimensional Endo-commutative algebras over F2. So they are giving classification over Z2, which has only 2 elements, 0 and 1. But in this paper, we are giving that classification of two-dimensional algebras and the commutative algebras over any field, including their result. We are generalizing their result. That their result will be just a very particular case of result in this paper.
I see.
That is one. Secondly, if go to, can you go to that? We are giving their algebra there. Just scroll up. One more. Here, no. Next slide. No. Previous. Here. You can see here. No. That next one. You can see theorem 13. In theorem 13, you are classifying Z2. It is exactly that their result. You can see here these algebras. But this after comments are a comment is given. That algebras given in 26 are represented by this list. So that correspondence between in theorem 13 and that in 26 are given in that comment after the theorem. You can see here. Because that algebras are denoted by C subindex. C4, C3, C1, C2, and so on. We are giving them in matrix form, matrix of spherical constant form. So this is a correspondence between them. That algebras and that our algebras and their algebras. So that means exactly we are reproducing their result by theorem 13. All other parts also given some generalization of their results. That was important part of the research.
So, Prof, sorry, Mr. DIYORJON, maybe you can click the previous slide. Theorem 12. Theorem 12. Theorem 12, the generalized version.
Yeah.
Which is the generalized version, the alpha, isn't it, Prof? The theorem 11.
Yeah, you can see theorem. No, this theorem 11 is classification of characteristic not 2, 3 case. But important thing is characteristic that theorem 12. You can see here in theorem 12, we're considering field characteristic 2, but it is not Z2 because a lot of field with characteristic 2 except for Z2. So Z2 case is given by theorem 13. But in theorem 12, we are giving classification for all fields with characteristic 2.
So this is a very good result, Prof.
Yeah, this is generalization because
very good result. Because
yeah, thank you.
the result generalized the previous paper, isn't it?
Yeah. We're generalizing that result, which is Japanese algebraic result, is generalized much due to result obtained recently by doctoral, which complete classification of two-dimensional algebras over any field.
So, Prof, is the result presented here published to any
We submitted already.
Oh, you're
Submitted the journal.
So congratulations, Prof. and Mr. DIYORJON.
It's under pardon?
Because you obtained the good result. So can we proceed to the next session, Prof? Photo session?
Sure, no problem.
Alright. So the participant, the attendance will be provided after the photo session. So please, participants, to all of the participants here, I sincerely hope that everyone will turn on the camera because we want to capture your image, okay? Your picture. Okay. All right, so get ready, everyone. Please post thumbs up. Okay. Okay, 1, 2, 3, smile. Ada ke ni? Right. So we have captured your image. Oh, the attendance list. Please wait a minute. I will share the QR code to all of you. Okay, this is the QR code. You can scan the code to get the e-certificate, of course. And for UIPM staff, you will get the UIPM training hours. So for international participants, I really hope that you can fill in the attendance link. Share. You are sharing. Okay. So, alright, so I think this is the end of session 8. Before we end the session, let me share with you one quote by SUZILA, an American author, salesman and motivational speaker. He said that if you are not willing to learn, no one can help you. If you are determined to learn, no one can stop you. Till we meet again for the next session. Have a great weekend. Assalamualaikum and bye. You may leave the meeting now. So thank you very much for attending this webinar.
All right. Thank you very much.
Thank you, Prof. Thank you, everyone.
Thank you.